In this video, I'll be looking at objects that are accelerating, focusing on velocity versus time and acceleration versus time graphs. Let's look at an object that is accelerating. Here is a cart released from rest at the top of an angled ramp. After being released, we expect it to speed up as it's going to move downhill. And because it's starting at 0 meters and ending at 6 meters, it's increasing its position by positive 6 meters. That means it's moving in the positive direction. But we're graphing this as velocity versus time, and it's released from rest, so our starting velocity should be at 0. A moment later, the cart is moving in the positive direction with some velocity, so I'll put my data in the positive quadrant, and a time later near the bottom of the ramp, the cart is moving even faster, so we're going to have an even larger velocity still in the positive direction. And because this ramp is constantly sloped, I would expect the cart to speed up at a consistent rate, and we get this nice linear graph. Now let's go a step further. I just made up a data table that supports the graph. Here you can see the velocity increasing by 1.5 meters per second every second, and the goal is to write a mathematical model that describes the data and the graph. Well, because the graph is linear, I can start with y equals mx plus b. Y variable is v, velocity. My x variable is t, time. And using the data, I get a slope of 1.5 meters per second squared and a y-intercept of 0 meters per second. Well, right now these are just numbers. Now we're going to talk about what they mean. Let's use a couple examples to try to figure them out. In the first example, we have two carts placed on identical ramps. The red cart is released from rest, while the blue cart is given a little push down the ramp and starts with some velocity VO. Now, since both of them will travel downhill, I expect them both to pick up speed as they travel. I'm going to try to graph both of their motions on the same velocity versus time graph. First thing I'd be looking at is the y-intercept. Red would start at the origin 0 meters per second because of being released from rest, while blue gets some velocity in the positive quadrant at the beginning, a little higher up than is red. Because they are on identical ramps, I would expect them to pick up speed at the same rate from that point, so we're going to get parallel slopes for the rest of the graph. In the second example, we again have two carts, but now both are released from rest, and they are placed on ramps with differing slopes. The goal again is to put data for each cart on the same velocity versus time graph. Well, now they would have the same y-intercept because they are both released from rest. They should start at 0. I would expect blue's slope, though, to be steeper than red's because it is on the steeper ramp, and it should pick up speed at a faster rate. The last two examples were to help us get a better idea of what the slope and y-intercept meant for our velocity versus time graph in our mathematical model. We can now conclude the slope as being the acceleration of the carts. We know this because it's measured in meters per second squared, and it's related to the rate of change of velocity. The y-intercept will represent the initial velocity. We know this because it is measured in meters per second, and this is the value of velocity when time equals 0. Let's take a moment to summarize what we know about velocity versus time graphs. There are three ways to extract numbers from these graphs. The y-intercept helps us with initial velocity, the area underneath the data helps us with displacement, and the slope represents the acceleration. Next, let's look at a sample problem. Here we're analyzing 4 different velocity versus time graphs, lettered A, B, C, and D, and the goal is to answer the 3 questions at the bottom of the screen. If you want to pause the video and try this yourself, I'll talk you through the answers here in a little bit. Question 1, we're trying to draw the corresponding acceleration versus time graph for each of our velocity graphs. We've already talked about the slope of the velocity graph as being a way to analyze acceleration, so that's what I'm looking for this question. Graph A has a constant positive slope, so I'm drawing an acceleration that is positive and constant. Graph B has a constant negative slope, so my acceleration is a constant negative value. Graph C, we're back to positive, and graph D back to negative. So for drawing acceleration versus time graphs, looking at the slope of the velocity graph is an easy way to go. Question 2, we're trying to answer if the object is speeding up or slowing down. Remember that the origin is where v equals 0, and that's the slowest you can go. So for graph A, the data is starting at 0 and getting away from 0. That must be an object speeding up. Graph B, though, is approaching the origin. It's approaching a value of v equals 0, so that must be slowing down. Graph C, again, is approaching the origin or approaching 0, so that should be slowing down as well. And graph D, again, starting at the origin and leaving, this must be an object that is speeding up. So to answer the question of speeding up or slowing down, Look at how the line behaves with respect to the origin, or where velocity equals 0. Question 3, we're determining if the object is moving in the positive or negative direction. That would be the difference between having a positive velocity or a negative velocity. Well, graph A is entirely in the positive quadrant. All of its velocities are positive. This is an object moving forward or in the positive direction. Graph B is the same. Even though the line behaves differently, the data is still in the positive quadrant, and this object is moving forward as well. Graph C is in the negative quadrant. All of those velocities are negative. This must be an object moving in the negative direction, and the same is true of graph D. So to answer the question of moving positively or negatively, focus on if the velocity is positive or negative, and therefore which quadrant the data is in.